All right then. So yet another bunch of problems. That's the objective of the class today. And so the sheet titled Electrostats, some more problems. Let's look at these problems. The first problem, which is about a solid uniformly charged sphere of outer radius r1 and inner radius r2. This region is uniformly charged. This region is uniformly charged and the total amount of charge in this region is Q. We want to be able to, and then there are three regions. Region 1, which is this cavity. Region 2, where all the charge resides. And region 3, outside the sphere, right? We want to be able to find the electric field in regions 1, 2, and 3. Now, look, this uniformly charged region could be imagined to be composed of thin spherical shells. Yes or no? A large number of thin spherical shells starting from r equal to r2 to r equal to r1. This, for example, is an intermediate shell. Right? And charge is uniformly distributed inside the shell. Clear? Now, if charge is uniformly distributed on a spherical shell, do you realize that it produces zero electric field inside? On the surface of a sphere, conducting or non-conducting, that does not matter. If you distribute charge uniformly on the surface of a sphere, then it's going to produce zero electric field everywhere inside and a region of constant potential within the sphere, right? It so happens that a conductor, when you give it a charge, conducting spherical shell, if you give it a charge, it gets uniformly distributed because sigma inversely proportional to r. And a sigma inversely proportional to r kind of a distribution, whether on a conducting surface or a non-conducting surface, is going to produce zero electric field everywhere inside. So this is one constituent shell of this region and it's uniformly charged, right? So everywhere inside this, it's going to produce zero electric field. All by itself, it's going to produce zero electric field everywhere inside. For points outside this shell, you can imagine this charge to be concentrated at the center of the shell. Yes or no? Yes or no? Now, so each of these shells, in this cavity, all these shells would be outside the cavity, and each of these shells will produce zero electric field inside the cavity, and therefore will produce a region of constant potential inside the cavity, right? So in region 1, the electric field produced by each of these shells is zero, and therefore the total electric field in region 1 is going to be zero. Yes or no? Right? Now, Let me look at region 2. This is the center C, the center C. So now I will look at small r greater than R2, less than R1. That's in the annulus, that's in region 2, right? For that region, let me look at in that region, let me examine a Gaussian surface centered at C, spherical Gaussian surface and of radius r commensurate with this condition, right? Again, out of symmetry considerations, can I not say that the electric field at every point of this would not only be of equal magnitude, but would be directed radially outwards, yes or no? Can I say this? And therefore, inside this small r, the total charge enclosed by epsilon naught must be equal to the flux passing through the surface. What's the flux passing through the surface? Since E and N are parallel at every point of the surface, so the total flux passing through the surface is going to be E into 4 pi r squared, right? So for region 2, flux passing through this choice of Gaussian surface, E into 4 pi r squared, that must be equal to charge enclosed. Now, realize that there is no charge up to R2. That means there is charge only from R2 to R. That means charge in this region, in this annulus, right? There is no charge inside the cavity. And the volume charge density for this region, which is the same, is like Q by 4/3 pi R1 cubed minus R2 cubed. That's the volume charge density in this region. So the charge in this chosen sphere would be volume charge density rho into this volume, right? So would be volume charge density rho into the volume 4/3 pi r cube minus R2 cube. Yes or no? Where rho, we already know Q by this, and you would then know E as a function of small r, where small r is about points in region 2. Yes or no? So that will give you the electric field in region 2 as a function of small r, distance from the center. Clear? Okay. Now let's examine region 3. You are an occasional visitor to the class. Yeah. When you get bored at home, you come to the class? No? Nevertheless, I hope you're doing good with your music. Playing your guitar or synthesizer properly? Sing. All right. Now, region 3. That means points outside. Points outside. Clear? So far, so good? Right? All's fair? Now, hey, if I look at a point P at a distance small r from C, that means Cp is small r, right? Then for the sake of this point P, this uniform volume distribution could be imagined to be a charge kept at the center Q, because each of these shells could be replaced by a charge at the center C of the shell. So this entire charge could be imagined to be concentrated at the center C of this region, solid charge region, and therefore the field at this point, which belongs to region 3, is going to be given by E in region 3 is going to be given by K times, there is a total charge Q at the center divided by R squared. That's the electric field in region 3. What do you say? Let's look at the next problem. Did you get it right independently also? All the parts of the problem? Very good. Problem 2. Okay. We have a conducting sphere of radius r with two spherical cavities. Clear? This is a conducting sphere with center A, radius r. And there are two cavities. There is a cavity, one spherical cavity inside this, where a charge QA is kept at the center. A is the radius of this cavity, right? And there is so there is another cavity. There is another cavity of radius B, and at the center of this cavity a charge QB is kept. Right? The rest is conducting material. Right? A is the center of the bigger sphere, where QA and QB are kept at the centers of the cavities. We want to be able to find the electric field and potential at a distance small r from the center A outside this, and at a distance small r from the center of B but inside this cavity. This is what we need to find out. But even before we do all of it, let's understand, in the event there is charge QA and QB kept at the centers of these cavities, how would charges appear on various surfaces that are involved here, right? First of all, this QA would induce what? Minus QA on this cavity walls, right? This QA would induce minus QA on the cavity walls. Minus QA on the cavity walls, right? My contention is that this would be uniform distribution. This would be uniform distribution because this QA and this minus QA together have to take responsibility to produce zero electric field everywhere outside this cavity. That means it should be possible for me to imagine this minus QA to be at the center of this, then that minus QA and QA at the center would produce outside the cavity indiscriminately a zero electric field, and therefore a uniform electric field is a must, so that this minus QA could be imagined to be at the center of this cavity. What do you say? Right? So uniform distribution. However, if QA was not at the center of the cavity, then this distribution would be non-uniform. Also, if this was not spherical but some irregular shape, then also minus QA would not be uniformly distributed on the cavity walls. That has to be understood without ambiguity. Okay. Now whatever I have said of this is also true of this cavity. QB at the center of this would uniformly distribute minus QB on the inner surface of this. Yes or no? So this QB there is minus QB uniformly distributed. But if QB, I repeat, was not at the center, then this wouldn't have been uniform. Right? Now, the conductor was electrically neutral. So this minus QA and minus QB appearing on the cavity walls would release QA plus QB on the outer surface of this bigger sphere. Yes or no? So QA and QB, QA plus QB would appear on the outer surface of this spherical conductor to maintain electrical neutrality of the conducting material. So on this surface, QA plus QB would uniformly appear. Now, this QA plus QB would take what kind of a responsibility? Everywhere inside this region, it must produce zero electric field. And when can a charge distribution on a surface produce zero electric field? If it is sigma inversely proportional to R. But R is the same at every point of the surface, and therefore sigma must be the same, and therefore QA plus QB must be uniformly distributed on the outer surface. That means for all points outside this, if this distribution is uniform, I could imagine QA plus QB to be concentrated at A. Right? So this distribution is uniform. However, I again repeat, if this was not spherical but some irregular shape, then this would not have been uniform because R is different at different points. So sigma would be different at different points so that it could produce indiscriminately zero electric field everywhere inside. Yes or no? Now, for points outside, say if I have a point P outside, that means AP is small r, and I want to be able to compute the electric field and potential at P. It's going to be because of this and the cavity and its contents, right? So electric field at P is going to be one that is created by this. For the sake of P, which is outside the sphere, this QA plus QB could be imagined to be concentrated at A. And therefore the electric field produced by this, just this outer charge, is going to be K times QA plus QB divided by R, where small r is greater than the radius of the bigger sphere, by R squared. Right? And cavity and its contents will produce zero electric field everywhere outside the cavity. So they will not count. So this is the net electric field at P. Right? And its direction would be like this. AP cap. AP cap would be the direction of this electric field at P. Clear? Now, the potential at P. Again, same thing. If I have to compute the potential at P, then that's only going to be because of the charge distributed on the outer surface. Right? I can imagine that to be concentrated at the center. So that's going to be K times QA plus QB by R. Now, as far as the cavity and its contents, they are producing zero electric field everywhere outside. That means they must be producing everywhere outside the cavity, they must be producing a uniform potential, right? However, look at this. This plus QA and this minus QA could be both concentrated at the center. So it's as if there is zero charge at the center, and a zero charge at the center outside this cavity is going to produce zero electric field and zero potential. So potential also, because of the cavity and its contents in this situation, would be zero. Bolo. Right? So potential because of the two cavities and their corresponding contents is going to be zero. That's the net potential at P. Yes or no? Right? Now, there is another part to this problem, which is inside B, I take small r less than B. Small r less than B is inside this cavity, right? I want to be able to compute the electric field and potential. Clear? But so far so good, right? No issues with this. So just let me focus on the cavity B. This is cavity B, just drawn separately. There is QB at the center, and there is minus QB uniformly distributed on the cavity walls. Right? And there is a point that I select inside this cavity, there is a point P that I select inside this cavity at a distance small r from the center of this cavity. From the center of this cavity, I select this point small r. I want to be able to compute the potential at this point, the electric field at this point, right? Now let me come to the potential at this point. Potential at this P, because of the cavity and its contents first. Because of QB, it's going to be KQB by R, right? Now, if there is charge uniformly distributed, then the potential that it produces on the surface is potential inside, because this uniform distribution all by itself will produce zero electric field inside, right? So it produces a region of uniform potential inside, yes or no, right? And so at every point, be it this point or this point, it produces the same potential, zero electric field. QB does not produce zero electric field at this point, but this charge will minus QB will produce zero electric field everywhere inside the cavity, a region of uniform potential. Now, what's the potential that it produces? Potential on the surface of this, because of minus QB alone, is going to be K times minus QB divided by the radius of this sphere. Yes or no? No, not the end of the story. There is potential because of this cavity. However, this cavity and its contents everywhere outside will produce zero potential and zero electric field. But this has no contribution at this point P. This second cavity will not contribute anything to P. However, look at this QA plus QB. This QA plus QB on the outer surface all by itself will produce zero electric field everywhere inside and a region of uniform potential. What potential does QA plus QB produce on the surface of this? K into QA plus QB divided by capital R, and that's the potential that it produces anywhere inside, including the point P, right? So then this is like K times QA plus QB divided by R. What do you say to this? That's the net potential at the point P inside this cavity, right? Now, the electric field at P. At P, which is a point inside this cavity, this charge will produce zero electric field. This cavity and its contents will produce zero electric field. At P, this uniform distribution on the shell, on this inner surface, will produce zero electric field. So the only electric field at P is because of this QB. So it's going to be KQB by R squared, right? That's going to be the only electric field at P, yes or no? Right? So the electric field at P shown is simply because of this QB is going to be KQB by R square. What do you say to this? Is that all right or not all right? This one? Yeah. See, potential at P because of QB is going to be KQB by R. Now, this charge is uniformly distributed on this spherical surface, right? Which means a uniform distribution on the spherical surface will produce a region of uniform potential. Now, what's the potential that this produces on the surface of this? K minus QB by P. And that's the potential it produces at P also, right? Now, this cavity and its contents will produce zero electric field and zero electric potential outside this cavity. Whereas this produces zero electric field everywhere inside. Therefore, it produces a region of constant potential inside. The potential that this produces on the surface of this sphere is going to be KQA plus QB by capital R, and that's the potential it delivers at P as well. So this then is the sum total of all the constituents of the potential at P. Right now? Make sure you stay conducting with conductors, okay? This is the most conceptual aspect of electrostats. Easy now. I don't think there is room for ambiguity after this set of discussions that we have had in the past as well, right? You should be very comfortable with all these ideas, isn't it? Let's look at the next problem. Okay, then there is another part. Okay, what is the force on QA and QB? Boo, 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 boo. 0, yes, absolutely. Look at this. This minus QA produces 0 electric field everywhere inside this. So QA, okay, this QA plus QB produces 0 electric field everywhere inside this. And this QB and minus QB produces 0 electric field everywhere inside this. So at the location of QA, the rest of the charges produce 0 electric field, and therefore QA experiences no net force. So does QB. QB also experiences no net force. Simple as that, right? 0 force. And if there is a point P here with charge capital Q, what's the force that this experiences? Huh? Yeah, E at P, which is K, QA plus QB by AP squared into capital Q. Because the field at P is only because of this charge distributed on the outer surface. Cavity and its contents will produce 0 electric field at all P's outside the cavities. Clear? At the center of this region, this is a conducting region. This is a conductor. This is a cavity inside the conductor, right? The conducting layer has inner radius A and outer radius B. And a charge small q is transported from O to infinity through, let's say, a very small orifice made. Through a very small orifice that is made, which will not affect things otherwise, small enough to not be effective in producing any change relevant, right? Through a very, very insignificantly small orifice, this charge q is transported from this to infinity. And it is done very slowly. When it's done very slowly means there is no addition of kinetic energy to the charge. We then want to be able to find the work done. When they say find the work done, means work done by the external agent. Means final potential energy minus initial potential energy of the system will give me the work done, right? So when it's transported to infinity, then the potential energy at infinity, which is the final potential energy, is 0. So the only task ahead of us is to be able to find the potential energy at O, when the charge is at O, right? Yes or no? Now, look, when the charge is at O, it's going to induce minus Q on the cavity walls, uniform. Yes or no? Minus Q would be induced on the cavity walls, right? And there would be leftover residual plus Q uniformly distributed on the outer surface, right? There is going to be plus Q uniformly distributed on the outer surface. Plus Q uniformly distributed on the outer surface, right? Now, I want to be able to calculate the total potential energy of this system. Clear? This Q here with minus Q here and plus Q on the outer surface, all uniformly distributed. I wish to compute the potential energy. Now, if you focus and concentrate on this, then the potential energy of this configuration would be 1. There is self energy of these two spherical surfaces. If charge q is uniformly distributed on a spherical surface of radius r, then it has self energy which is kq squared by 2r. If charge q is uniformly distributed on a surface of radius r, on a surface, not inside a volume, then remember its self energy is kq squared by 2r. Yes or no? Have I told you this before? Right? So then, this has self energy, this shell has self energy K minus Q whole squared by 2A. Again, this spherical surface also has self energy. How much? KQ squared by 2B or not to be? To be? Also to see. Okay. Right? Now, look. This charge Q and this charge minus Q will have an interaction energy. How do you calculate the interaction energy, let's say, for this? By the way, suppose there were two charges, just to revisit that, if there were two charges, and I wanted to calculate the interaction energy of the two charges, what is it that I did? All that I did was, let's say I computed the potential at one of them because of the other one. Say potential at this point because of this was what? KQ1 divided by R separation into this charge. That's the interaction energy. Or I could have computed the potential at this point because of this KQ2 by R into Q1. So KQ1 Q2 by R, that's how you compute the interaction energy for discrete collections, right? Right? So then, if this be the case, then say if there is Q here and there is minus Q there, radius small a. Now, and this has minus Q uniformly distributed. What's the potential on this because of Q? KQ by A. Right? KQ by A is the potential on this because of this into the charge minus Q. That's going to be the interaction energy of this Q and this minus Q. Yes or no? KQ into minus Q by A. Right? Now, there is also interaction energy between this Q and this plus Q. So, this Q and this plus Q, if this was Q and there was plus Q uniformly distributed on radius B, then the potential on this is going to be KQ by B into Q. That's going to be the interaction energy of this and this. So, which is like KQ by B into Q. That's interaction energy. There is one more interaction energy. These two surfaces, right? So, there is minus Q on this and there is plus Q on this. This is A and this is B. This minus Q and this plus Q, they have interaction energy. So what I could do is, I could compute the potential on this because of minus Q into Q. What's the potential on this because of minus Q? K minus Q divided by B. That's a potential on this because of this into the charge Q. Yes or no? I could have done this. Or I could have said, instead, I could have also computed it as potential on this because of this. Now, what's the potential anywhere inside this because of this? KQ by B into charge minus Q. Either way, it's going to give me the same value. So, that's the interaction energy of these two entities, right? So, which is K times minus Q into Q divided by B. That's the total self energy plus interaction energy, and therefore that's the total initial energy. That's the total initial energy. Work done by the external agent is going to be UF minus UI, right? Work done by the external agent is always UF minus UI plus change of kinetic energy. But change of kinetic energy is 0. So it's simply going to be UF minus UI, where UF is 0 and UI is this. What is the work done by the electric field even if kinetic energy is added? Even if kinetic energy is added, work done by the electric field will always be negative of the change in potential, negative of UF minus UI. Even if kinetic energy is added, this will always be the work done by the electric field. Clear? Okay. Problem 4 is about match the column. Right. So there is column 1. In which we have the following situations. A. There is plus Q on a shell. This is uncharged, no charge. This is shell 1 and this is shell 2. There is a key, electrical key. B, this one is bigger and this one is smaller. In this case, this is small and this is big. In case B, the only difference is this is big and this is small, and there is plus Q on this shell. And this is the key which could be deployed for connectivity. This is shell 1 and this is shell 2, right? This is B. And there is no charge on this. C. There is a situation like this. There is plus Q. This is shell 1. This is shell 1. And this is shell 2. There is plus Q on this. And there is on shell 2 there is no charge. This is C. And in D, this is shell 1, this is shell 2, and there is plus Q on this, and there is no charge here. No charge here, right? These are the various situations. These are the various situations. And column 2, P, charge flows through the connecting wire. Q, potential energy of the system decreases. R, no heat produced. S, sphere 1 has no charge after equilibrium is reached. All right, right? Okay, this one is shell 1, shell 2. Obviously, this is at a higher potential compared to this. So, charge will flow till such time that their potentials get equalized, right? So, there is flow of charge. So, P is true for this. Now, when there is flow of charge, there is a current generated through this wire, connecting wire. If there is a current generated through the connecting wire, there must be Joule heating. There must be heating, right? Joule heating. If there is Joule heating, that means there is some loss of energy. Where does it come out of? It must be at the expense of loss of potential energy. So for every time there is a flow, there must be loss of potential energy. So for this, Q is true, potential energy of the system decreases because there is loss of energy in the form of Joule heating. Loss of energy in the form of Joule heating. Joule heating, that energy has to come from somewhere, na? It has to come at the behest of potential energy. Therefore, potential energy must get slashed. Right? The difference in potential energies, initial minus final, will give me the extent of heat which is dissipated because of the current flowing through this. Right? Q is true. Obviously, R is wrong for this. Heat is produced. Sphere 1 has no charge. No, there will be flow of charge from higher to lower potential. So, S is not true for this. Okay. So, P and Q for this option. Let me look at this. Same thing. Whether big sphere or small sphere, there will be flow of charge till such time potentials get equalized. This situation and this situation are identical. So the same set of conditions, P and Q for this as well. Now, look, when I join these two this time, they will be, realize, if you recall, this entire thing would be like one single conductor. The entire charge will go on to the outer surface. Remember this? This discussion took place. So this entire charge would flow on to the outer surface. Remember that? This entire charge will rush to the outer surface. This was a discussion that took place sometime, right? And therefore, this shell 1 will have no charge. And of course, there would be flow of charge. P is true for this. Q is true for this. And S, sphere 1. Yes, sphere 1 has no charge. So S is also true for this. P, Q and S are three options true for C. Yes or no? Come to this. See, the potential of this is KQ by outer radius, and that's also the potential anywhere inside this. So potential of this is the same as potential of this. So if I connect this, there would be no flow. If there is no flow, no heat generated, no potential energy decrease, right? And shell 1 has no charge. So the only option, this is not true for this, this is not true for this. No heat is produced. That is true because there is no flow of charge. R is true for this and S is true for this. Yes or no? R and S are correct options for D. Right, Manan? In the XY plane, there is the circle of radius R. Just say radius R of the circle, centered at this point O. This is the center of the circle, and there are two dipoles here. A dipole with dipole moment P times I cap here, and a dipole with dipole moment root 3 times P j cap there. These are two dipoles. Okay. Let us first of all reduce this system to a single dipole. Not difficult. If there is a dipole P here and a perpendicular dipole root 3P there, then the net dipole is going to be the resultant of these two, which is going to be root 3P squared plus P squared, which is 2P. Is the net dipole? Yes or no? And if this angle is theta, then do you see that tan theta is root 3? Theta is therefore 60 degrees. Theta is 60 degrees. So, first things first, this entire thing could be replaced by a single dipole (2p), making an angle 60 degrees with the x-axis. Right? Now, if you recall, there is a dipole 2p, and if I look at any point at an angle phi with respect to 2p, let's say this is r, then the potential at this point is given by what? K times the magnitude of the dipole moment cos phi, where phi is the angle made by this radius vector with 2p into cos phi divided by r squared. Right? Yes or no? For a given small r, if small r is fixed, then V would be maximum when phi is 0. For a given small r, V would be maximum when phi is 0. Now, if I look at various points on this circular path, then for this 2p, realize that this would correspond to phi equal to 0. This point A would correspond to phi equal to 0. Yes or no? So the potential at this point A is going to be K times 2p cos phi, which is 1, divided by r squared. At all other points, cos phi would be less than 1 and the potential would be different, it would be less than that at A. So potential on this circle would be maximum at A. Right? So this is going to be the maximum potential that appears on this circle. Maximum potential on the circle. Potential because of the dipole on the circle is at A. Minimum at what point? See, at this point B, at B what is phi? Pi. What would be the potential at B? Cos phi, which is minus 1. Right? So K times 2p by minus r squared. So minimum potential at B? Yes or no? Right? Now, let me look at a diameter perpendicular to the 0 phi line. A, B, let me say these are C and D. These points are C and D, which is perpendicular to this, say. Perpendicular to this. So C would be about phi equal to pi by 2 and D would be about phi equal to minus pi by 2. Yes or no? This is 2p plus pi by 2 and this would be minus pi by 2. Right? Now, at C and D, what would be the potential? 0, because cos plus pi by 2 or cos minus pi by 2 would be 0, right? So potential at C would be potential at D, each would be 0 because phi would be either plus pi by 2 or minus pi by 2. Yes or no? Right? Now, so far so good, right? See, put electric field in the radial direction is given by what? Kp, say in this case, K times 2p cos phi by r cubed for any point on the circle. Small r will be capital R, right? So, at C and D, phi ER would be 0. So, ER is 0 at C and D. Now, what gives me E phi? E phi, that means the tangential component of the electric field is going to be K times 2p, and sorry, this is 2 times K2p by, right? 2K, P is 2p, cos phi by r squared, right? That's the result for the radial. So, in the phi direction, K times P sin phi by r cube, that's the electric field in the tangential direction. And realize that E phi would be maximum in magnitude at phi equal to plus minus pi by 2. Yes or no? Right? Huh? Right? So now, once we have some of this data, let's start looking at various things here for this. Okay. The coordinates of a point on the circle where potential is maximum. Potential is maximum at A. What would be the coordinates of A? R is the radius, R cos 60 degrees and R sin 60 degrees. So the point A is R by 2 and root 3 R by 2. Sorry? So the point A where the potential is maximum, coordinates of A would be R cos 60, R sin 60 degrees. So R by 2 and root 3 R by 2 are the coordinates of the point where potential is a maximum, right? The coordinates of the point on the circle where potential is 0. So A matches with P. A matches with P. R by 2, R, okay. Now B, coordinates of a point on the circle where potential is 0. Now potential will be 0 for phi equal to plus and minus pi by 2. Right? Potential is given by K times 2P cos phi by R squared. That's the potential at any phi with respect to the dipole. Yes or no? So when phi is plus minus pi by 2, potential will be a maximum. And do you realize the point D? This is 30 degrees. What's the x coordinate of the point D? R cos 30 degrees. Y coordinate is minus R sin 30 degrees. Yes or no? Right? So the point D has coordinates R cos 30 degrees, which is R root 3 by 2 and minus R sin 30 degrees. That means minus R by 2. Yes or no? At C also the same thing happens. See, as far as C and D are concerned, you know, their x and y coordinates, the sign changes, right? For C, obviously, x coordinate would be minus R root 3 by 2 and plus y coordinate would be R by 2. Yes or no? This length will be the same as this length. This is 30 degrees. This is also 30 degrees. This length will be the same as this length. These would be the coordinates of C. So at these 2 points, you will have potential equal to 0 at phi equal to plus minus pi by 2, right? Coordinates of points on the circle where magnitude of the electric field intensity is 1 by 4 pi epsilon naught. Magnitude, that means plus or minus, is this. See, whenever cos phi is plus or minus 1, it will become 4 kp by r cubed into plus 1 or minus 1. When is cos phi plus or minus 1? When phi is 0 or pi. That means when phi becomes 0 or pi, the electric field ER would assume a value 4 kp by r cubed in magnitude, because E phi at these points, wherever cos phi is 1 or minus 1, sin phi will be 0 and E phi will become 0. And that means at points A and B, that is phi equal to 0 and phi equal to pi, E phi becomes 0 and E would be simply ER and would have a magnitude 4 kp by r cubed. Right? So at C and D, we already have found the coordinates of A and B. If XA and YA are the coordinates of A, then minus XB minus YB will be the coordinates of B. Right? Coordinates of point on the circle where magnitude of the electric field intensity. Yes. Magnitude of the electric field intensity, we want to be 2 kp by r cube. That will happen when phi is plus minus pi by 2. That means at which 2 points will you have the net, and wherever phi is plus minus pi by 2, ER is 0, the net electric field would be E phi. And when would that happen? When phi is plus minus pi by 2. Plus minus pi by 2 means? Right. The point C is plus pi by 2 with respect to this line. The point D is minus pi by 2 with respect to the dipole moment direction. So at point C and D, we have electric field intensity given by K into 2p by r cube, because ER will become 0 at these points. E would be simply E phi. Is that okay or not okay? At the point A, there is a charge plus Q. At this point B, there is a charge plus Q. This distance is D, and this is very far away, so AB is a large distance. B is imparted an initial velocity U parallel to AC. Find the minimum distance of plus Q from capital plus Q during the motion, given various things. Q is this, etc. We'll just write down the equations. Hey, realize when you imparted velocity, then this is the line joining the two charges. This velocity would have a component like this, parallel component, and will have a component perpendicular to the line joining the two charges, right? Electrostatic repulsion would impede U parallel. U parallel will go on decreasing, right, because of electrostatic repulsion. And you would therefore expect after a while U parallel to become 0, right? But as long as U parallel is non-zero, the distance between the two charges will go on decreasing no matter what the trajectory is, because this parallel or non-zero U parallel will cause decrease in relative separation AB. So when U parallel becomes 0, then that would be the closest distance between the two charges, right? So you can expect that after a while, when it's imparted, this is, let's say, the trajectory. After a while, U parallel will become 0, U joining the two charges will become, along the line joining the two charges will become 0, and we'll only have U perpendicular left. The net velocity then would be simply perpendicular to U parallel, right? And there would be further electrostatic repulsion which will keep the distance between A and B ever growing, right? So at a point of shortest distance, the minimum between the two charges, the net velocity of the particle must be perpendicular to AB. Now, I want to find d min. I want to be able to find d min. First of all, it's a conservative field. I can apply conservation of energy, and the total energy at this point is only kinetic. Why? Why? Because this separation is very large. So potential energy is 0. There is no interaction between the two charges. This is 0, right? At this point, the separation now becomes finite. In addition to kinetic energy, there is also potential energy. How much potential energy? Q divided by d min is the potential energy between the two charges. So K times capital Q into Q by d min, plus there is kinetic energy, half mv squared. That's energy conservation. Energy principles, yes or no? No, it's in a horizontal plane. Assume that it's happening in a horizontal plane, right? Keep this whiteboard horizontal and imagine the whole thing, right? Now, again, the force that B experiences because of A, the line of action of that force will always pass through A. Therefore, it will produce no torque about A. The force acting on B because of A will produce no torque about A, and therefore angular momentum about A of B must be conserved. Angular momentum of this moving charge about this point is conserved. Why? Because the force acting on B because of A will have its line of action always pass through A, will therefore never produce any torque about A, and therefore the angular momentum about A must be preserved, right? So what's the initial angular momentum about A? M U into D. That must be the angular momentum about A in this case, which is mv into d min. You can eliminate V from these two equations and solve for d min. You can solve for d min. Is that all right? Number 7. If I have a region in which electric field is known as a function of x, electric field varies in the x direction, then the volume charge density as a function of x is epsilon naught dE dx. Remember this? Have I discussed this result in the class? Right? In this case, E as a function of x is given to be ax squared plus bx. So this is epsilon naught dE dx, which is 2ax plus b. That's volume charge density as a function of x. A result which I may not have shared with you, but which would be required for the next problem. Let me get you past that result. So far so good, right? Not a problem. See, the small area dA on the surface of a conductor. This is a conducting surface. Part of a conducting surface. Say this is part of a conducting surface. And there is a certain point P on this conducting surface and a small area surrounding P, a small area dA surrounding P, a small area dA surrounding P. Clear? And say on this, at this point P, the surface charge density is sigma. At this point P, the surface charge density is sigma. Now, can I wipe this off? Small, but I'm just drawing an accentuated view. So this is the point P. This is the point P, right? And on this dA which surrounds P, this is that dA that surrounds P, right? The surface charge densities in a small area surrounding P is sigma, surface charge density. So now you know that the field just outside P, we have learned, is going to be sigma by epsilon. The field just inside P is the inside of the conductor, E is going to be 0. Yes or no? Right? And this sigma by epsilon naught would be along the normal to the conductor at P. And the field inside the conductor, this point just inside the conductor, is going to be 0. Yes or no? Now, see, if I look at a point just outside P, there is electric field at this point because of two things. One, because of this charge, just outside P, because of this charge, the charge on dA, and because of charge on the rest of the conductor, E because of this dA, E because of dA surrounding P, and E because of the rest of the conductor. That's a net electric field, right? Say, just outside P, this is the inside of the conductor, that's the outside of the conductor, right? Just outside P, we have electric field E1, which is field because of charge on dA surrounding P. How much is that charge? That charge is sigma into dA, where sigma is the surface charge density at P, right? And there is going to be field due to the rest of the conductor. Field because of the rest of the conductor is E2. Yes or no? So just outside P, the electric field is E1 because of the charge on this dA plus E2 because of the charge on the rest of the conductor, and this must add up to sigma by epsilon. That's the net electric field just outside the conductor, just outside P, right? Yes or no? E1 is because of the small charge element at P. Now, I look at a point just inside the conductor. This is the inside and this is the outside. Let me look at a point just inside the conductor. See, as far as this point A and B are concerned, as far as these points A and B are concerned, the electric field at A, because of this is almost like a point charge. This is almost like a point charge at A. The electric field because of the point charge at P is even like this. B is on the opposite side of A. So the electric field at B because of this point charge just inside is going to be even downwards, yes or no? See, if there is a point P and I look at a point A, this is a point charge, just above and just below. Because of this point charge, if the electric field at A is E1, then on the opposite side of P, it's going to be E2, E1, it's going to be E1 downwards, yes or no? Do you all understand this? Have I confused you? No? Because of a point charge on opposite sides of the point charge, the electric field will be in opposite directions. Yes or no? Even upwards and even downwards for A and B. Now, as far as the rest of the conductor is concerned, which is very large compared to P, this is the rest of the conductor, which produces at A an electric field E2 upwards, right? Now, this very large conductor has no way to distinguish between A and B. Right? Very large conductor. This is a very large conductor. And whether I look at this point A or just a very nearby point B, if at A there is an electric field E2 produced like this by the rest of the conductor, then at B also the electric field would be E2 produced like this. Because for the large conductor, A and B are almost indistinguishable. Right? So at B, the electric field because of the rest of the conductor is E2 upwards because of the rest of the conductor, and E1 minus E2 must be 0. E1 must be equal to E2, therefore, because B is a point inside the conductor, so the net electric field inside the conductor must be 0. So the net electric field at B must be 0, or E1 must be equal to E2, where E1 is the electric field produced just because of the charge at P, E2 is the electric field produced by the rest of the conductor just outside or just inside. And E2 turns out to be E1 equal to E2, each would be sigma by 2 epsilon. Yes or no? Now, look, this charge element surrounding P, this is a small charge element which is sigma into dA surrounding the point P. sigma into dA surrounding the point P. A charge will never experience a force. This charge will never experience a force because of its own electric field. A charge will experience a force only because of the field produced by the rest of the charges. So if I look at this sigma dA, will it experience a force because of P1? No, it will experience a force because of E2. Right? So if I have to calculate the force on this charge element surrounding P, then that's going to be sigma into dA into E2. Sigma into dA. E2 is the electric field produced by the rest of the charges. So the force on this charge element is going to be sigma into dA into E2. Right? Which is like E2 is sigma by 2 epsilon naught. So this force dF then is rendered sigma squared by 2 epsilon naught into dA. That's the normal force acting on this charge element, small charge element, normal force acting on this charge element, dA, which means force per unit area on this charge element, outward force per unit area, dF dA is the force per unit area on this charge element. That turns out to be sigma squared by 2 epsilon naught. So just outside a point P, this charge element at the point P will experience an outward force, outward electrostatic force, and this outward electrostatic force per unit area, referred to as electrostatic pressure at the point P, is sigma squared by 2 epsilon naught. At P, if the surface charge density at P is sigma, then at P there is an outward electrostatic pressure which is trying to pull it out of the surface, is sigma square by 2 epsilon naught. If sigma is different at different points, then the electrostatic pressure would, sigma squared by 2 epsilon naught, would be different at different points in general, right? So whenever there is charge distributed on the surface, it has a tendency to be pulled out of the surface. And that electrostatic pressure at any point where the surface charge density is sigma is given by sigma squared by 2 epsilon naught. Right? This is an important result. Sigma squared by 2 epsilon naught electrostatic pressure at a point where surface charge density is sigma, outward pulling force. Right? Important result, must remember this. And now the next problem is an application of this. Oops, no, that's all right. I'll pick it up. Thank you. So we are talking of problem 8. Two hemispherical shells. This is the separation. This is one hemispherical shell, thin, very thin. This is one hemispherical shell, and this is another hemispherical shell. Two hemispherical shells. This is one hemispherical shell, and this is another hemispherical shell. This is the common plane of the two shells. AB is the common plane of the two shells. And there is a negative charge minus Q naught at the center of this region, and there is a total charge plus Q. There is a total charge plus Q distributed uniformly in this region, right? Very clearly, any point on this will experience an outward electrostatic pressure, but will also experience attraction from minus Q naught. If the electrostatic pressure is more than the electrostatic attraction, right? Any charge, any point here, say any point here, right? It will experience an electrostatic pressure which is sigma squared by 2 epsilon naught, surface charge density at P by, because of its own charge. Electrostatic, right? Because of the charge on this entire surface, sigma squared by 2 epsilon naught, right? And will experience this charge element, will also experience electrostatic attraction from this. However, if the electrostatic pressure outward is more than the attraction, then the two shells will separate. For them to be in equilibrium, the electrostatic pressure must be less than the attraction, must be less than the attraction. The attraction should be more than the repulsion of this element, so that the two shells are kept in position. Yes or no? Now what is sigma distributed on the surface of this? Sigma is Q by, say the radius is 4 pi. This is very thin, so let's say the radius of this is r. So Q by 4 pi r squared is the surface charge density on this shell. This is almost, I can imagine this to be on the surface only, because it's very thin. It's very thin. So entire thing on the surface. Q by 4 pi r squared is the surface charge density, right? Now, if sigma is the surface charge density at this point, then this is electrostatic repulsion, electrostatic pressure, outward electrostatic pressure. Outwards and at this point there is an electric field because of minus Q naught, right? What's the electric field because of minus Q naught at this point? K times minus K times Q naught divided by R squared. That's the electric field at P. At P, because of minus Q naught, at P, because of minus Q naught, there is going to be an electric field KQ naught by R squared. That is force per unit charge acting at P, right? KQ naught by R squared is the, right? Now, so KQ naught by R squared is the force per unit charge acting at P into charge per unit area acting at P is sigma. This is charge per unit area at P. So this is force per unit charge into charge per unit area is force per unit area, yes or no? This is force per unit charge, that's the electric field, into charge per unit area. So this is force per unit area, which is electrostatic pressure inwards, which is electrostatic pressure inwards, right? So this KQ naught by R squared into dA into sigma will give me inward electrostatic pressure. Right? For equilibrium, this is inward electrostatic pressure. This is F2, the outward electrostatic pressure. F1 must be greater than or equal to F2. Inward electrostatic pressure must be greater than or equal to the outward electrostatic pressure. That must be the requirement towards equilibrium. Which means, what is F1? F1 is this. F1 is KQ naught by R squared into sigma. That must be greater than or equal to sigma squared by 2 epsilon naught. That's the condition for equilibrium. This will get cancelled, and then we have this k is 1 by 4 pi epsilon naught r squared. Q naught must be greater than or equal to sigma, which is q by 4 pi r squared into 2 epsilon naught, right? 4 pi epsilon naught r squared would get cancelled, so you must have q naught greater than or equal to q by 2. This will maintain equilibrium of the two hemispherical shells, right? So, continuing with electrostatics, some more problems. Problem 9. Two small equally charged spheres of mass m are suspended from the same point by silk threads of length L. Each of mass m. The distance between them is x, much smaller than the length of these threads. They carry charge q, which leaks out from them, Consequently, if it leaks out, then their velocity of approach turns out to be a by root x. We want to find the rate at which dq dt happens. Rate at which charge leaks is going to be dq dt, given that there, see, if charge did not leak, then they would be brought to equilibrium. The separation between them will not change, they will have no relative velocity of separation. But since charge is leaking, they are continuously acquiring newer equilibrium positions, right? We want to be able to find the rate at which charge leaks in order that the velocity of approach between them is a by root x, where x is the instantaneous separation between the two charges, right? Now, see, once again, easy to see at any given instant when this has charge q, mass mg, weight mg acting downwards. This is the separation between them. This is x by 2, this is x by 2 halfway. Say if this angle is theta, this is also theta. Right? For each one of them, the electrostatic repulsion, right, is taken care of by component of tension, right? Say if T is the tension here, then T sine theta will take care of electrostatic repulsion and T cos theta will balance the weight. Yes or no? Right? So T sine theta, if Q is the charge on each one of them, then T sine theta is kq squared by x squared, right? And T cos theta takes care of weight, which means the equilibrium is given by theta such that tan theta is kq squared by mg x squared, right? Kq squared by mg x squared. Now, this length is L. What is sine theta? Sine theta is x by 2L. That's sine theta. X is much smaller compared to L. So sine theta is small. So sine theta is approximately equal to tan theta. Because sine theta is very small. Sine theta will be equal to tan theta approximately. So then this tan theta can be replaced by sine theta, which is in turn equal to x by 2L. Which gives me x cubed is some constant c times q squared. X cubed, see, k into 2L by mg is some c, right? This c, to make it algebraically decent, k into 2L by mg is c. So x cubed is cq squared, right? Now dx dt would be the velocity of approach, because x is the relative separation. Then dx dt would be the relative velocity of approach, right? And dq dt would be the rate at which charge leaks. Clear? So if I differentiate this both sides with respect to time, if I differentiate this with respect to time, x cubed is cq squared, c is known. Then 3x squared is 2cq 3x squared dx dt is 2cq dq dt, right? Dx dt can be replaced by v by root x, right? V by root x or a by root x. Dx dt is a by root x. That's the relative velocity of approach into 3x squared is 2c. Now this q, I need to write everything in terms of x, is it? They want everything in terms of x. So this q I can write as x cubed by c, square root of that, right? Square root of that, and this is dq dt, and you can solve for dq dt from this equation, the rate at which charge is leaking. Clear? Problem 10. There is a thin charged ring of radius r centered at O. The total charge on this ring is Q, uniformly distributed, and we have an infinite line of charge like this. This is an infinite line of charge with linear charge density lambda. With linear charge density lambda, we want to find the interaction between the force between the ring and the thread. This is the thread. We want to find the force between the ring and the thread. So what we'll do is, we would find the electric field at any point on the thread, the force on that, and we'll sum it up from x equal to 0 to x equal to infinity. So if this is the thread, O is x equal to 0. At any point P on the thread, I take a small element. This is a point P chosen at a distance x. The electric field at this x is going to be given by kqx by r squared plus x squared to power 3 by 2. That's the electric field at this x. And if I choose a small element dx, then the charge on this element would be lambda into dx. Exposed to this electric field, that's the upward force df on this element. The total force on this line of charge is going to be sum of all of this, where x runs from 0 to infinity. That will be the total force on this line of charge. The ring will experience an equal and opposite force downwards. right? And easy to integrate, because see, this is r square plus x square to power minus 3 by 2. Derivative of this is 2x. Function raised to a certain power into the derivative of that function kind of form. And this will give you the total force on the thread upwards. And the same force will act on the ring downwards, right? Now, there is a ring of uniform, non-uniformly charged charge per unit length, lambda equal to lambda naught cos theta. Say this is a ring, and it has a variable lambda charge per unit length on it. So this is some x-axis from where thetas are measured. So which means if I look at a point, this is the center, if I look at a theta like this, then the lambda at this theta is going to be given by lambda naught cos theta. The lambda is this theta will be given by lambda naught cos theta, right? We want to be able to find the electric field at the center of this ring. We want to be able to find the electric field at the center of this ring. Clear? Now, because of this charge, what would be, say, the electric field at O? The electric field at O is going to be, that means if you place a unit positive charge, it will experience repulsion from this. I take, let's say, a small element on this, which is d theta. That means this length would be r d theta. The charge on this, dq, is going to be lambda, which is lambda naught cos theta, into r d theta. That's the charge on this chosen element, right? And the electric field that you witness here, dE, is going to be k dq by r squared. K dq by r squared is going to be the electric field at this point, dE, which is like k times dq, which is lambda naught cos theta r d theta by r squared, right? Yes or no? Now, these d's are all in different directions. So you can't say the total E would be sum of all these d's, right? What you do is you take an element at minus theta. This is minus theta. This theta is actually minus theta. And the lambda here will be the same as lambda here. See, because replace theta by minus theta, you get the same value of lambda. Yes or no? That means these 2 points at O will produce the same dE, same magnitude of dE, because cos theta will remain the same. So the 2 symmetric elements at theta, and this is minus theta, theta and minus theta, will produce the same dE this way. Why? Because it's the same value of lambda. Lambda naught cos theta, lambda naught cos minus theta will give me the same cos theta, right? So dE. Now, for these 2 elements, the vertical components will cancel off. So for every theta, there is going to be a minus theta, which will cancel off the vertical component of dE. So only the horizontal components of dE's will get added up. So all that we need to do is, we need to sum up only the dE cos thetas. We need to sum up only the dE cos thetas, starting from theta equal to 0 to theta equal to 2 pi. Theta equal to 0 to 2 pi only. If I said theta equal to 0 to pi, then I would take 2 dE cos theta. This is it. And the net electric field, therefore, would be E this way. Is going to be E this way. That's the E net. Easy to integrate, right? All that you will have to integrate is, see, k, lambda naught, r squared will all come out. Cos theta into cos theta, d theta, cos square theta, which you would write as half 1 plus cos 2 theta and integrate, which would be theta plus sine 2 theta by 2, etc. Supply the limits. That will be the net electric field, and it's going to be horizontal, right? The last two problems I have solved in the class, right? So I can skip those. Now, one thing that I want to mention as a remark. Can I wipe this off? One remark which is important. See, if there is an infinite conducting plate, thin conducting plate, infinite, very large conducting plate, okay, and this is thin, say this is thin, and I placed a charge q at a distance d from this thin plate. I placed a charge q at a distance d from this thin plate. What will happen is, it will induce a negative charge on the nearer surface and a positive charge on the surface away, right? There would be attraction between this q and this minus q, and there would be repulsion between this q and this plus q. But the attraction will be more. So there will be a net attraction. There will be a net attraction between the plate, which was neutral. The plate is neutral. Between the plate and q, there is going to be attraction, right? Yes or no? Now, suppose I earth this plate. Now, suppose I earth this plate. Then the free positive charge will flow onto the earth. Earth will always absorb the free charge, that is fine. This is bounded charge. This is bounded by this plus q. Earth will let it go. But the free charge, it will assimilate, right? Now, the attraction will further increase. The attraction will further increase. The moment you connect an entity to earth, its potential becomes zero. Its potential becomes zero. Earthing means reducing it to zero potential. Why is earth looked upon as zero potential? See, very simple. See, this is the earth. This is the radius of the earth, right? And you give it charge q. Then, suppose there is a certain amount of charge q on the earth, right? Then, the potential of the earth would be kq by re. Re is very large. Re is very large for the earth, right? So, this becomes zero for the earth. Potential of the earth is zero. You connect something else to earth, the earth will reduce its potential to also zero. Sabko hero bana dega. This is what earth does, right? Now, this is the result that I want to tell you. This system is actually equivalent to, let's say, this is the point where the plate is kept. This system is equivalent to a charge q, a charge minus q, placed at B, which is A and B are mirror images of each other about P. This is D, this is D. Then do you realize that if there is a Q here and a minus Q here, that will reduce the potential of P to zero? That means effectively it will be simulating this plate, right? So a Q here and a minus Q equidistant will create the plate situation, a region of zero potential. Let me tell you a result which is called the method of images. Method of images. which is like the force of attraction between this plate, grounded plate, earthed plate, and this charge q is the same as the force between this plus q and its mirror image about the plate. This is the mirror image about the plate. The force between these two charges would be the force of attraction between the plate and q, and that's going to be k. The force between these two charges, as you can see, is this by d whole square. That's the force between these two charges. This is the force of attraction also between the plate and the charge q. The grounded plate and the charge q will have a force which is the same as the force between the charge q and its mirror image about the plate. This is called the method of images. It's not exactly there in your syllabus, not in the IITJ syllabus, but sometimes, nowadays they've started giving just about anything. So they don't care about, what they have documented in syllabus. They just throw their arms here and there, freeze it, and they give anything. So, might as well know this result. It's an easy thing. Know this result. If you have to find the force of attraction between q and the plate, what you do is create a mirror image of q about this plate, which is a charge minus q, and the force between this q and this minus q would be the force between q and the plate, force of attraction between the q and the plate. If the earth was not grounded, then the force of attraction would be less than this, because there would also be repulsion from these positive charges. So force of attraction will reduce. Know this.